Okay, this is lecture 15 by Harvey Friedman on invariant maximality derivations, please.
Thank you. So today we're going to talk about section 3.6, but a little background just to make sure we're all on the same page. Remind you the entire updated reversal in one link only now, all the other links erased, is on the downloadable manuscripts page. And I put lecture notes for the last lecture of the June 12th in 3.4 to 3.5. Chapter 3 is what we're talking about with the derivations, is on my downloadable lecture notes page. I haven't put any material except the old version of the intro on chapter 3 in my downloadable manuscripts page. So there's nothing right now on the downloadable manuscripts page on chapter 3, polished stuff, but I'm cleaning up stuff from 3.1 to 3.5. So the plan is I'm going to have 3.1 through 3.5 pretty polished on the downloadable manuscripts thing, say this weekend. And then this section 3.6 I'm talking about today should be on there early uh, early in this coming week. We're getting warmed up. Okay, so let's go. First of all, I keep changing things a little bit. So the new title of the book is you may not notice it's even new. Invariant maximality, comma, choice, comma, and games. Invariant maximality, choice, and games. So that's a kind of a smooth running title. And it really means invariant maximality, invariant free choice, turns out, and invariant finite games. All right. Anyways, invariant maximality, choice, and games. And the structure of the book is these chapters: introduction, invariance in real functions, that hasn't changed, invariance maximality derivations, invariant maximality reversals, those haven't changed. 4 is the reversals, 3 is derivations we're doing now, and 5 is invariant finite choice, which is a new title, but there's already some form of it on the downloadable manuscripts page. However, this is getting better, but there's some expositional, at least, advances in this that are not present yet on invariant maximality on the downloadable manuscripts page, but will be some point, and then invariant finite games, which I haven't really started to write a draft on. But with game theory, as is common, some things actually obtain a special kind of simplicity that, once you pay the price for going to games, and if you're a game lover, that's not a price, that's a joy. Um, some nice things happen when you go to games. All right, so the table of contents is being fooled with a little bit here and there for this chapter 3. I now have a good draft of the introduction, but not for the whole of chapter 3, but for quite a bit of chapter 3 beyond where we are right now. And order equivalence, order invariance, we talked about. The lead template, I think this is all the same. General constraints, order constraints. So there's the boldface theory. There's the boldface theory, which makes good sense with maximality, but the boldface theory doesn't make any sense with invariance. It doesn't make at least no obvious sense with invariance. However, the light phase version, order constraints, order invariant constraints, does make sense not only with maximality but also with invariance, right? And this is the key to invariant maximality subject. And then we actually combine the order constraints maximality with the invariance, and we get invariant maximality, but only for one particular version called the lead template, which is the strongest one, by the way. But then we have seven secondary templates. So this is all review, but every time I say this, I think I'd say it better. So there's five general, this is bold-faced, squares, roots, free sets, cliques, and independent sets. Um, and these are all shown to be, well, no, okay. These are all shown to be special cases of the general constraints. These five secondary templates. Uh, Templates means that the function that's being used is a parameter. The function is a parameter, the little f. Uh, and for the reversal in chapter 4, we used one particular little f. All right, so and this is the extra two. The extra two don't make good sense or don't make as good sense as the others unless you're in the light-faced version. So this is the light-faced. This is light-faced. And then, of course, this is all fine with maximality, but then we want to put the invariance in. So now we have 7 variations of the order constrained version of the lead template. And then we prove that all of these are equivalent to each other, and all of them are equivalent to, in fact, the lead template with order constraints. But I've been underestimating how hard that is to show, and I think I now have it under control. That's one of the reasons, the main reason why I didn't put 3.1 through 3.5 up yet, because I want to get a completely correct proof of that they're equivalent to the big one, the lead template. Okay. Now, there is actually a slight technicality here. The emulator form, which is very important educationally, I used it for high school, as I mentioned to you, and high school in 2 dimensions of cardinality 3. So I can just do everything by hand. I don't have transfinite theory for them. Um, Uh, but the template, I have had a hard time showing that that template is equivalent, that template is as strong as the others, unless I assume the function has a fixed point, just at least one fixed point. But I don't, invariant maximality lives on plenty of fixed points. So it's a minor glitch, which I haven't been able to get rid of, but it's a minor glitch. Emulators could be weak uh, if the functions are. Let's not say it that way. And I know emulators are strong, given the same large cardinals, because the functions I use it on are uh, have fixed points, plenty of fixed points. It's just that the general theory where I'm looking at any little f seems to need that f has a fixed point. Um, so there's some interesting things there that are open. Uh, the variant maximality for all these things give me what's called the 7 secondary templates, and as I said, we'll have all equivalents with the full one. Then last time we did usability. Usability means can you use it? And there's usability flat out, and then there's usability in each dimension. So for a particular dimension K, you can consider usability, uh, which is an important idea. Now, one usability is special. One usability is completely analyzed and has nothing to do with large cardinals. One usability is handled simply with RCA naught. one usability. And one usability, the lead template, the lead one, is it's stronger. Is I'm not talking about logical strength. I'm just talking about stronger implication. Is stronger than the one usability for the seven um, for the seven secondary templates. All the seven secondary templates have the same one usability, but the lead template has a stronger one usability. Okay. All right. Now I cleaned I made some improvements in here. You know, everything in invariant maximality except for the when I get to explicitly pi 0, 1, everything is only implicitly pi 0, 1, not explicitly. But there's something you can do with implicit pi 0, 1. It's not something to be only embarrassed by, namely falsifiability. And I think we discussed this, but I made some improvements on this. The general theory of falsifiability. You're falsifiable in T if T proves that if you're false, then you're provably false in T. So obviously, anything that's pi 0, 1 is falsifiable because if it's false, you have a sigma 0, 1, and therefore provably uh, true, right? So, and in fact, if it's implicitly pi 0, 1, it's obviously falsifiable. The trick is, does falsifiability imply implicit pi 0, 1? That would make implicitly pi 0, 1 much less of a slight embarrassment, right? Well, that's not, they don't quite match, but they almost match. They match when you have the complete, that they match when T has full induction. That's the rough story. They match it completely when T has full induction. All right, but in any case, we have that usability is implicitly pi 0, 1. If the if the function you're asking about usability for is order theoretic. Order theoretic meaning in the elimination of quantifiers for q comma less than dense linear ordering, those concrete ones. All right, so today we're going to talk about finite usability, and there are four parts to this. I don't want to touch, I'm still fooling around a little bit with the perfect setup. I don't want to touch the main events. You know, the main event is usability with respect to infinite functions, functions whose domain is infinite, and they're very simple functions. So we won't talk about 3.7 today, but we will talk about it in a week, 3.7. And then we're off to the races for the core of this is the absolute, core events in invariant maximality. Different levels of set theory are apparently needed. I don't have any reversals except for the top one, are apparently needed for various fragments. This should be familiar to you. This is, well, with K equals N, this should be familiar to you because that's what was reversed. Okay, and then I'm going to do more because I have a lot of things going, getting more, analyzing more functions, whether they're usable or not. This is going on now as we speak, so that's why I wrote more. So I don't quite know the scope of this chapter 3. It might be very pleasantly surprised uh, to be able to analyze all almost identities or order theoretic functions. I might well be able to do that. But it's a little too early. I may be able to only handle some cases. Then I close the chapter with 16 equivalences of the lead statement. 16 equivalences, eight that we talked about before with two variables, K and N, 8, and then the one where N and K are equal. The one with N and K are equal is nice because there's only one quantified variable if K equals N. And that's the one that's reversed. The one that's reversed is one of the 16. And we leave the whole chapter knowing that all of these are equivalent to each other. They're under RCA naught, all of these are equivalent to each other. So when we pick just one of them that we reversed, we're happy. All right. So now the finite case, the case of usability for a finite function is claimed here to be completely solved reasonably elegantly with a lot of stability, as you shall see. So let f be a finite function. You remember the double colon means partial function. The following are equivalent: to be usable, to be fully two usable. Usable means you can just use it. Well, I explained down here again, just in case you forget about it. Fully usable is a little weaker, is weaker than usable because it's only in dimension k equals 2. And two usable, fully usable is the same as usable, except it's dimension 2. And two usable means that those seven alternative secondary templates hold, all 7. And when you say all 7, you can actually just use 5 of them, are just as strong dimension-wise from each other. But dimension-wise, they're not as strong as the lead templates. Yeah, so, all right. So, and the serious condition. So here's the necessary and sufficient condition. F is strictly increasing, and you don't have either of these two things, which I will describe in a second. I mean, formally you see it. We showed already that, okay, we did show already that that this was necessary. These are necessary. That was done last time, I think. Yeah. All right. So what do these things say? The first one says that f goes up from -1 and it goes up to 1 from something. So this is the picture. The first clause means F goes from my thumb to my forefinger, and also from my thumb up here to my forefinger here, which is at 1. F goes from -1, which is my thumb, to my forefinger, and this goes from my thumb to 1, up to 1. Okay. By the way, these could cross either way. Okay, that's what that condition means. And the other one is the other way around. This forefinger goes to the thumb, and this forefinger goes to the thumb, which is at -1, and my forefinger up here, which is at 1, goes to my thumb, which is lower. Okay, I'm saying that those fail, that you get an obstruction. If either one of those hold, then and then by the way, they're equivalent to each other by inverse. You take the inverse function. And we proved before that last time that usability is invariant under taking the inverse of the function. All right, so those are obstructions, and those are the only obstructions. So this was proved last time, and it has to be strictly increasing. So it has to be 1, 1, which means that this makes sense. So the issue is, how do I show that 4 implies 3? That's the weakest one. How do I show that 4 implies 3? That's the only thing left. All right. Now, let's just recall F is usable if and only if order constraint have maximal things that are F invariant. Every order constraint has a maximal solution, has an F invariant maximal solution. F is fully 2 usable if and only if every order constraint on 2-dimensional sets uh, has a maximal solution that's F invariant maximal solution. F is 2 usable if and only if, just pick this one, this is as strong as the others for the secondary ones, that every order invariant relation has a root, as an F invariant root in 2 dimensions. The relation is on pairs. And of course, the function we're talking about for the templates are partial functions on this space. Okay. Now, it's obviously suffices to prove 3 and 4. Yes, I said 3, 4, 1. So it's just a matter of showing 4 implies 3. It's all a matter of showing 4 implies 3. So here's what I do. In the section 362, we assume finite F. This is for finite F. Of course, the necessities, by the way, these necessities are for any F. The necessities are, but the sufficiency is only for finite F. After all, we're not using we're only using RCA naught. By the way, I say CIFA because if you remember this convention, if you have a statement that's just existential, just existential infinite thing, if you can give a defined solution that CIFA proves uh, holds, then I say it's provable in CIFA. So this is better than saying RCA naught. CIFA is strong exponential function arithmetic. Everybody knows what EFA is, right? I mean, I think it's called EA or I sigma naught or of X, depending upon who else you talk to. But you talk to me, it's EFA. Strong EFA means the indefinite exponential, like in Ramsey's theorem for arbitrary dimension. You need iterated power of 2, k times, where k is a variable. All right, so that's CIFA. Uh, all right, in section 6362, we assume F is strictly increasing, has no fixed points, and 4 holds. So we're putting some more conditions on, and we show that uh, if F has cardinality at most 1, or F can be extended to what I call a finite, we show that if F is strictly increasing, has no fixed points, and condition 4 holds, then either F has cardinality 1 or it can be extended to what I call a finite radial function. A finite radial function. Then we show that every finite radial function is fully usable. Actually, we only have to show that it's 2 usable. Yeah. All right. We actually just show it's fully usable. Why not? In section 364, we put all this together and prove our theorem, finite use. Our theorem of finite use, which is all those 4 equivalent. All right. This is just restriction. This is just notation of the most obvious kind. Field is domain, union range, graph is that. All right, functions of cardinality 1. A function of cardinality 1 looks like this. It just says f of a equals b, and that's the end of the story. If a function is of cardinality 1, then I can use it. And this is easy once you have the right idea. And it's sketched here. Uh, first of all, S is F invariant just in case A through A is in S, if and only if B through B is in S. That's a definition of invariance in this case, right? We just want to show that equivalence. So there are two cases. The first case is uh, oh, let's see, why did I say it this way? I guess that's all right. If the A's and B's are okay, maybe I meant these two separated. A through that just singleton A. No, no, no. I meant this. Yeah, and I didn't say this right. It's better to say just the set consisting of A and B to the R is contained in E. Yeah. Then let S be any maximal extension of these two with S to the R contained in E. Right? You can do that. Right. Oh, okay. So yeah, so I have made this this is of length K. These are of length K. These two things are of length K. And I need to look at all the R tuples built from these things. So they're just from A and B. I need to know that uh yeah. No, these stay as blocks. I'm sorry, these stay as blocks. So I'm looking at R tuples of K tuples. I'm looking at R tuples of K tuples. This should probably be explained a little bit better. R tuples of K tuples, yeah. And I'm saying that they're all contained in E. Then I can just throw them in right in the beginning of the construction and then extend in any way. And I know I'll have F invariance because I'll have this is an S and this is an S. Yeah. These refer to the obvious R tuples of K tuples. Yeah, I'll probably say that better in the official manuscript. Okay. Then I can just take any extension. I've already forced this to be invariant right at the beginning. And then I suppose this is not the case, that I'm blocked from putting both of them in. Then I take any number C between A and B such that then for any number between A and B strictly, these will also be blocked. So then why don't I just put this in here in the front, start the construction with that. Then I've made sure that I'm going to get invariance for the other reason, namely that these are also going to be uh, not in S, because this one blocks this one. So so they can't be in S. And so therefore they're both negative. So therefore the equivalence holds. Okay, that's all there is to this. And if B is bigger than A, so remember we had this is not what I mean. B is smaller than A. And if B is smaller than A, you do the same. The same argument holds. No, no, it's no different. Okay. This next section is that I want to extend to radial functions. The whole point is that if I have a radial function, and I have to describe what that is, it's a simple idea, a little technical. If I have a radial function, I can, in fact, it's usable. Radial functions are usable. So if I can extend to a radial function, I know I'm usable. Now, everything is equivalent up to isomorphism. I mean, these concepts are standard, are kind of just order theoretic concepts. So I have to make sure that I can extend to radial functions if I obey that sufficient condition, that allegedly sufficient condition in the theorem thin use that we're trying to prove. I need to show that I can extend to radial functions, and then I'm done. I don't to show the radial functions are usable. All right, so radial function means it's finite, strictly increasing, has a unique fixed point. -1 and 1 are in the field, and the structure, this structure, -1, 1, graph of f, you can't put less than in there. -1, 1, graph f has a strictly decreasing automorphism. H from -1, 1 to -1, 1. Okay, the canonical examples are the function I divide the interval into two n parts, equally spaced, the arithmetic progression from -1 to 1, right? This set here. And this is the partial function that maps that makes the negative numbers more negative and makes the positive numbers more positive, right? Just by increment 1 over n. And of course, it will have the fixed point 0. We'll have the unique fixed point 0. And it's strictly increasing, clearly, right? And it has a strictly decreasing automorphism given by additive inverse. All right. Strictly decreasing automorphism, which is the additive inverse, right? So this is a typical example of a radial function. I mean, a canonical example. And pretty much this is more or less the form it has to have. And you can show that this is usable. This is a usable thing. You have to prove that, but it's not too difficult, and that's the last step in this proof. Okay, and I use graph f here. I don't want to get involved in partially defined functions when I'm talking about structural issues if I can avoid it. So I just look at the graph, which is a two-dimensional object. Okay, so there has to be some infrastructure developed about radial functions that they actually do what they're supposed to. So P is the unique fixed point, and H is any strictly decreasing automorphism. Oh, I did put less than back in there. Yeah. Is that right? I always get confused by this. A less than B. And that's not right. Right, because minus doesn't do that. All right. H and H inverse are strictly decreasing bijections from -1, 1 on to -1, 1. These are supposed to follow from just being radial. H inverse is an automorphism of this. Automorphisms are closed under inverse. So H and H inverse map the graph of F onto graph F, domain of F onto domain of F, range F onto range F. All of this is trivial. H circle H is strictly increasing. Right, you can get that formally from H being strictly decreasing, right? And H circle F has to be the identity on field F. And they have to, H and H inverse agree on field F. Okay, so you have a nice picture. That's just, just like how minus works. Minus of minus. But that, but it's true more abstractly. Of course, H must fix the unique fixed point. H of minus one must be one. Remember, this is an automorphism and it's decreasing, so it's got to hit. It's got to hit one somehow, and it can only come from here. So H of minus one is one. H of one is minus one, and P, the unique fixed point, has to be inside, right? H restricted to field F is the unique strictly decreasing bijection of field F onto field F. Because you get this stuff simply because F is finite. And the field of F has to have cardinality 2n plus 1 for some n greater than or equal to 1, right? With n elements less than P and n elements bigger than P, where P is the unique fixed point. And F inverse is radial with the same P and H. Okay? Get this. I mean, I do that in gory detail, of course. All right, now, in this section, we work with these two things. Item one is the hypothesis in this is the sufficient condition we're trying to use, right? This is the sufficient condition. This is the necessary condition that we're trying to prove sufficient, right? Okay, and this is a consequence of one, which is not completely obvious, but which we do. From this, we get that either F is the function that maps -1 to 1 only. And since it's strictly increasing, if it maps -1 to 1, it can only be -1 to 1. Can't have any other arguments. Or 1 to -1. Or it can be extended to a finite radial function. And this is very good because we want to assume this and we want to get usability. We just proved usability for functions of cardinality 1, right? They're taken right here. And we claim we're going to prove later that if you extend to a finite radial function, you're also usable. So one implies two is the whole story, except we have to just check that the radial ones. By the way, radial meant included finite. Yeah, put that in there. Right. So that's all we have to do is show later that a radial function is usable, and then we already showed this. So we got to show one implies two, and I think there's some easy stuff in here that just, see what I say here. I mean, I took out the proofs. I just put the statements in. So the first thing is if one holds and -1 is not in the field, or 1 is not in the field, then 2 holds. In other words, what I'm really saying is that if -1 is not in the field, and 1 holds, then you can extend it to a radial one. Okay. And that makes sense because one says that you can't have this configuration, and that will ruin radial. That's obviously ruins radial. But you see, if you don't have anything at -1, you can just put stuff down here to make it radial. You see, that's the idea. You can put stuff down here to make it sort of like opposite stuff down here, so you can get the decreasing automorphism. You sort of copy stuff and reverse it. All right. So you're fine if you're missing one of the endpoints, then you can extend it to a radial. But now, what happens if you have both the endpoints? Then you have to be more careful. But if you have both endpoints, then f of -1 must be. Then you have the one of these possibilities. See, if you don't have these, then you're going to have these. Because one holds, you don't have see, this is reversing what was before. Okay, so if you just stare at this, you'll see that this is immediate, almost immediate. All right. Okay, so basically what we now have to do is show that if any of these hold, then we're done. Then we can extend to a radial function, or we're done automatically with these, right? With these, this makes the function cardinality 1. So we have to show that we can extend to a radial function if we have this. Okay? Either one of these. All right, so how do we do that? Okay, so f is a sharp function, so we have another kind of function. A sharp function means it's finite, strictly increasing, no fixed points, and we have this one here. All right? The other one is dual. The other one is dual, so let's not worry about the other one. It's the same arguments. So this is what we have, right? We're assuming that is this here. Okay. Okay. So we have -1 is less than f of -1, so it goes up, and then from here, somewhere it goes up. Not sorry. It goes up from -1 and goes down from 1. That's what I want to say. Goes up from -1, goes down from 1. See, it threatens to be a bit radial-like, right? And we just want to show that we can extend it to a real radial function. We're going to have to put stuff in, inside it. We're going to have to beef it up, okay? And that's what we do. Okay. So if I have a function that's like this, I can decompose it uniquely into f1 less than. Less than means this entire field is smaller than this entire field, is smaller than this entire field. But I think what I say here is even stronger than that. It implies what I just said verbally, namely that F is F1 union F star union F2, and these are disjoint. So these are disjoint. F1 is the restriction. F1 is the restriction of F as long as it's strictly dominating. See, we're strictly dominating at -1 and we're strictly regressive at 1, right? That's the hypothesis. That's up here, right? So the idea here is to take the initial segment of F, the largest initial segment of F on which it is strictly dominating, and the largest tail of F that's strictly regressive. Those are and this is what F1 and F2 are. And the stuff in the middle, see, it has to be in the middle. It can't start, if you just think about this, the rest of it has to be really in the middle, trapped in the middle like this, like the verbal explanation of this. In fact, here, just like this. -1 is less than the max of the field of F1 equals F of P1. is less than min of field of F star is less than max of field of F star is less than F of P2, which is the same as the minimum of field of F2, which is less than 1. And I'm actually just existentially saying that's the first sum. P1, P2. We allow F star to be empty. By the way, it could be that there's nothing in between here. In that case, min and max don't really make sense, so just omit them. Just remove them from the discussion. Yeah, am I gonna get rid of P1 and P2 as well? Yes, because these don't make any sense. So I think I have to say more here. Remove, even remove more than that. All right, let's not worry about this. I don't want to get bogged down. All right. So now we've got this decomposition, blah, and stuff in the middle and blah. And the stuff in front is very radio-like. Threatens to be radial, and the stuff at the end threatens to be radial. This is strictly increasing, strictly dominating and increasing, strictly increasing, dominating, strictly increasing, strictly dominating here, strictly increasing and strictly regressive here. And in the middle, it's doing crazy stuff. It's just increasing is all we know. So what we want to do basically is show that we can now it's pretty obvious if we don't have any of that wiggly middle stuff, we can make this radial just sort of trivially. You can make it extend it to a radial function. But the point is, what about the middle stuff in the middle? Does that cause any problems making it radial? Of course, the answer is going to be no, it doesn't cause any problems. You have to prove that, which I do. All right, so we have the following situation. This first part is strictly increasing, strictly dominating, and finite with -1 uh, in the domain. Right? That's what a star function is, just the first one. And we want to show that we can extend this. Well, we can extend it arbitrarily at any point. We have to show that you can do that, which is a little simple thing. And then if you're beyond f of -1, you can extend it so that p is a value. You have to show that you can extend it. You can extend it so that p becomes a value. If it's bigger than f of -1, it would have to be bigger than f of -1 in order to become a value. But you can do that and keep it being a star function. Keep it strictly increasing, strictly dominating, and finite. So this is some stuff about strictly increasing, strictly dominating, finite functions can be extended. And this is what you need. And you're closed if whenever you're bigger than f of -1, you're in the range. So in other words, when you put stuff in, you put the inverse in. You have to show that you can do that. No, that's the definition. Yeah, that's the definition of closed. And we're going to show, and we show that every star function extends to a closed star function by putting these points in. The definition of orbit is standard, Q, FQ to FNQ. Of course, we're interested in the maximal orbits, so to speak, maximal sets like this. The orbits form a partition of the field of F, and F is finite. the orbits form a partition. That's clear. I mean, an orbit might, so there's no fixed points. So the orbits are cardinality greater than one. Okay. So every star function extends to a closed star function, and every star function extends to a closed star function G, every closed function. F extends to a closed star function G, whose orbits starting at -1 ends at max of the field of F. See, what we're going to do is basically something sort of like arithmetic here that's going on here. And -1, F of -1 intersect the domain of F is the same as F and G agree, as F and G agree on this initial part. Okay. So this is another extension process that we want to throw in inverses. Okay. So we're trying to build a radial function. And this is a special kind of radial function we're going to get, namely an NM function. Uh, the number of points in the initial part of the function is n. There's an orbit that goes from -1 to the biggest possible thing in the whole thing, the max of the range of F. Well, the maximum of the range of F one. No, that won't be one. Uh, the max of the domain is one, but it'll be F inverse of one. Yeah. So there's an orbit from there of cardinality one higher, and every other orbit, uh, yeah. And the reason this is n plus one is the orbit will end, at, yeah, okay. I mean, that is slightly confusing. Every other orbit starts in the same place. You see, every other orbit starts in the same place. That's because we have this closure condition that we go back, and there's a cardinality m exactly, and there's just this longest one of cardinality m plus one. Oh yes, and this thing is not going to the top one. Remember, this is this is the function that starts that decomposition of length 3. See that decomposition of length 3. Here, we're talking about F1. That's all. We're just talking about F1, setting it up nice. Okay, we can extend to an NM function. Um, there's n things here making n different orbits. All of them have length m, except one of them length m plus one. This is like arithmetic, right? You think of these orbits as jumping along, as an arithmetical progression. These orbits are arithmetic progressions, right? Except this is abstract and order theoretically. Okay, so let F be a closed star function. I can find N and M. Okay, so here I can obviously build more and more of this kind of stuff and get it extended to an RR function, right? Not just N and M, just R. If you make R big enough, you can do that. Yeah. This follows from this because the star function can be extended to an NM function. So it's just a composition. Yeah. Now the RR functions are order isomorphic, i.e. these are isomorphic because it's forced arithmetic, with arithmetic operations. And then we can do it with with the going the other way. Strictly increasing, strictly regressive functions, we can do the same kind of orbit thing, okay? And that takes care of, in the three-term decomposition, it takes care of the outer ones, F1 and F2. There's the middle junk in there that has to be dealt with finally. All right. So this is the same thing, same thing. Now, I guess I didn't put any details in here. It's in the manuscript. Now I can actually extend to a radial function because I've got the essence of radial on the outer layers. Then there's this middle stuff that has to be dealt with, which is not a problem because there's no endpoints involved. You can pretty much do uh, anything you want in there. Yeah, I didn't keep it. I thought it was too technical. But the middle stuff, see, the middle stuff is enclosed, you see, and away from the other stuff. So you can do what you want in there. Um, yeah, I've forgotten exactly. I threw this away for the lecture, but anyways, the details will be up there early next week. Okay, and then you can go into minus. Oh, this is just, sorry. This is just doing the star function. I haven't talked about the middle crap. How do you handle the middle crap? Maybe that doesn't come up yet. Yeah. Yeah, okay, but I don't say here how I handle the middle stuff. It's uh yeah, all right. I'll make sure this is not a problem. Now, making them fully usable uh is first of all is pretty clear once I normalize it. And you can normalize it by making sure that they're finally strictly increasing. You can make zero the unique fixed point, right? If I'm talking about radial stuff. You can make the field the 1 over m, the I over m points. In other words, minus m divided by m all the way to plus m divided by m. And make the radial function actual minus. You have to prove that you can do this isomorphically. In other words, if you have any radial function, you can isomorphic it to this canonical one. You have to prove that. And every radial function is order isomorphic to a normalized radial function. And then you prove that every normalized radial function is usable. Uh, and that's an inductive construction uh, that's technical, but highly manageable, and everything's finite. So it's a finite. You do this on the integers. You look at all of the integers, and you do this on the integers. You apply Ramsey's theorem, and then after you're done, you can extend it arbitrarily so that it lives in the rational space. But you first do it in the integers, the double-ended integers. Yeah. And then you wind up with this because you prove this implies this, or even you just need this actually. That's all you need, and this was necessary, and this was done by showing by several steps that you could extend. That's either you either have f of you either have a function of cardinality one, or you can extend this to a radial function. And then a radial function is usable, and any restriction of a you can extend to a radial function, you're obviously usable. Because usability goes downwards. Okay, now this actually characterizes usability of finite functions just from the statement. You characterize usability, full K usability and K usability. But since we already handled one usability, we've actually characterized usability, full K usability and K usability. We've already characterized these. So we characterize pretty much everything we want to characterize, except if we go into much more detail and look at, say, emulators where the dimensions are off, from what I know. I think it's only the emulators, yeah. Then K usability has not been fully characterized for emulators. So that would be an open question. But uh, for all the other 7 secondary templates, we have characterized this no matter what K is, and also, of course, general usability. All right, I think that's it. Andreas, I'm done.